As part of the whole automotive industry and within Aston Martin, we've experiencing that over the last few years the programs are getting more and more compressed. Before we had 5 to 7 years to develop a whole vehicle program. Now we've been asked to have that reduced by 3 to 5 years, and also the expectation is for the quality of the product to go up. So clearly, on a traditional way of approaching an engineering problem, these two objectives are very conflicting. So what we're trying to do is to try to move into a virtual environment to try to have this both reduction in cost and reduction in time and resources, but also a step up in quality. We're trying to progressively move from a traditional engineering approach in the automotive industry to a more virtual environment and use vehicle models and use simulation tools to embed some of the traditional elements that you would do on a racetrack or on a proving ground or even on an indoor brake test, and try to bring it into a virtual model, so have a digital twin of the products that we're trying to develop and try to do as much work as possible within the simulation environment. We created a virtual model of the vehicle, and we were able to run through different elements of handling and ride behavior, engage our suppliers for tire models to have a good representation of the models, and then identify areas which would be error states that we wouldn't commonly find until we have the first prototypes, and put measures in place and correct it to get the best product available. There's many of them. So, for instance, when developing DVX, we realized that the basic kinematics and compliance of the suspension, there was some issues that wasn't accounted for because the grip that we requested from tire suppliers was higher than it would be typically for an SUV. So there was some rear axle instabilities that we managed to find out through simulation and through the use of simulators, and then put corrective measures. When that came into the first prototype, we were able to test that and confirm that if we had followed the traditional procedure, we would have a big error state into the vehicle. But by the point that we had the first prototype, we already had the corrective measurements, and then the car was in a better place. We have the offline simulation, where we sort of set the main guidelines of how the vehicle is going to perform, how the vehicle is going to handle, how the vehicle is going to ride along the roads. But there's ever so much that you can do in offline simulation work because you don't have that driver feedback. So the next step is having a simulator, and then you bring the driver and the human interface with the vehicle. For example, for DDX, when we were developing the active control system, the roll control of the vehicle, from offline simulation we identified some tuning and some algorithm, but then when it was tested by the drivers, they didn't like it because it was too aggressive and it felt too unnatural to drive. So then the simulator becomes very useful into further developing control systems to make them more natural and more along the lines of in this case, of Aston Martin's DNA. Now, for future programs, what we're trying to do is to have hardware in the loop embedded within the software in the loop, because we've identified that, again, the use of a simulator, having the hardware, it could be highly beneficial for doing the fine-tuning, for looking at the time responses of the actuators, looking at the delays of the network, and that at the end of the day has a big influence both in the final product and the quality of the product. What we've identified is that by the use of virtual tools and simulation, the expenditure profile is a lot more smooth, and it's also lower as you take throughout the life of the product. And that's because any error states that you find them at the very beginning of the program before you are committed to any tooling or you are committing to any production parts. So the cost is brought down quite drastically. The other benefit is that when it comes to the last prototypes, because we've covered a wide range in the design space, we narrow down that design space and therefore the number of tunables that we would need for the physical testing to sort of fine-tune and find the last few bits in the optimal solution is also reduced. We are always trying to be as cost efficient as possible, and that goes back to the very beginning when we're saying we're trying to reduce the time of the programs, and by reducing the time of the programs we're also reducing the cost of the programs.